Hey there, in this video I want to talk about the Crank-Nicholson method for solving partial differential equations. The Crank-Nicholson method is a close cousin to the FTCS method that we talked about previously. The difference ultimately is in the choice of how to do the time steps. FTCS, the forward time part, is forward Euler method. Crank-Nicholson does an averaging of a forward Euler and a backward Euler. It means it's a little bit harder to write the equations we're going to use. Like the part you do by hand is a good bit harder. It means that the equations become implicit. So instead of getting a single point for point solution for, let's call it y, the variable we're trying to find, we have coupled equations that we have to solve using some kind of linear algebra technique. Ultimately, we're going to find that we get things that are banded arrays. So we'll use SciPy solve banded to solve these equations. Now, that sounds kind of painful. Like, why do we do this? And the reason for that is there's some problems that crop up in some partial differential equations where the forward Euler method ends up being unstable. And so let's start with an example here. And that would be here the wave equation, which is the second partial derivative of y is proportional to the second partial derivative of y with respect to x. And we have this c proportionality constant, which is the speed of the wave. And if we run through the FTCS method, so we replace the space derivative with finite differences, and then we're going to get these equations here for v, the velocity. That would be like the derivative of y, to contrast that with the wave speed c. So we get the first derivative of v, or first derivative of y is v, and then y gives us these two simultaneous equations that we're going to then solve with the forward Euler method. Okay, so let's do that. And then when we're done, we're going to animate our result. I've pre-typed out the animation code just so you don't have to watch me make typos in the same block of code that I've done, like, I don't know, I feel like 3 times in the last couple videos. The only thing unique here is the limits that are going to apply, and these are pre-chosen to give us a nice looking graph. Okay, so to do our wave equation, we have to have some kind of speed. I'm going to pick 100 here, and then I'm going to pick a grid for my x's and t's. And to be fair, I'm picking these values because they become unstable very quickly. Now, that's not just because I picked bad values. It will eventually become unstable no matter what values I pick, but we might have to wait a while. Now, a side effect of that, or a consequence of that, is sometimes you can get away with just using FTCS if you don't need to simulate the wave for very long. It might stay stable or stable enough that it looks okay. That's kind of risky business because you can't be sure about your result. But sometimes that is good enough. Anyway, so what I'm going to do here is 101 spatial grid points, which is actually a pretty normal sort of thing. There's nothing too strange about these values. For time, I'm going to do kind of larger steps just because that makes it break quicker. So we're going to go from 0 to 1/100th of a second, and I'm going to do that in 1001 steps, which means that h would be equal to the final time, 0.01, divided by 1,000 steps. Or, well, you should be careful about the terms I'm using. 1001 points making 1,000 steps. We've talked about this before. Okay, so the next I need some initial conditions. So let's start with the wave, or the string, just being horizontal, just because that's easy to make and it gives me good boundary conditions that the wave has to be fixed at its endpoints. And then for v, I'm going to make up something a little bit more interesting. Let's represent striking the wave, so like we've hit it with a mallet. And there are different ways to represent striking, and this doesn't really change what the solution is going to do, but it does give us at least something that's nice and consistent with our boundary conditions. So the form I'm going to take is x times 1 minus x multiplied by exponential of negative x minus 0.5. This represents striking the wave striking the string in the very middle. And then divide by 100, which is kind of like a width of the mallet that hits it. Again, the actual form here is not especially important, just that it's some kind of reasonable function. And so anyway, what you'd imagine should happen if you take a string and you hit it in the middle is the string vibrates with some kind of frequency. So to make our animation, we want to archive the shape of the array at any given time. So this is basically an array of y's. And then for each time step, we want to stash the current shape, so with a y.copy. We also need to make a v copy. And this has more to do with the fact that we have these two equations that depend on each other. So let's say that I write the code in the same order I wrote here. Okay, so v depends on its old value and depends on old value of y's. There's no problem there. And then y depends on y and an old value of v. Now, if I've already changed v and I plug that in, I'm not really doing the right method. So I need to make sure I'm using the old value of v, which is why I do a copy here. So I have a copy to use. Okay, and now the next two lines will look like the equations here. So your typical FTCS sort of technique is to leave the boundaries alone and only use the middle of the array. And these are all written in a form that could be changed to a plus equals. So in this first case, plus equals h times c squared divided by a squared. And then multiply that by y to the right plus y to the left. And then subtract 2 times y. And 2 times y means not including the boundaries. Okay, now same sort of thing here for y. That's going to be the second equation up here. So y is a plus equals of h times v. But this is where we have to use that copy. It has to be the old value of v. We don't want to use the previous line's v. We want to use the original v, effectively calculating both v and y at the same time. And missing that is a very subtle, very aggravating bug to try to find, because it'll give you things that work. It just works differently than what FTCS was supposed to do. Okay, so let's make sure that this runs. Okay, and it seems to get through that pretty quickly, just doing 1,000 steps. And now let's see what happens when we animate it. All right, so there it is. It looks like we get, oh no. All right, so this is what instability looks like. For the first few time steps, it acts just fine. We've struck it, it's moving upwards like it's gonna vibrate, and then it just goes absolutely insane and the string like literally explodes because of the fact that the forward Euler method is unstable in certain circumstances. Not always, but in certain circumstances. Textbook goes into a lot more detail about mathematically when and why this happens. But the general rule is beware that it can happen with forward Euler. So our solution now is to do something different for our time steps. We're going to keep the code as similar as we can, but the fact here is this forward Euler is just not sufficient for our needs. So we're going to have to do something that's more stable. That's called the Crank-Nicholson method. Okay, so let's jump over and work out the math for how that goes. All right, so as we saw, the forward Euler method didn't really work out for us. So what I want to do here is compare the forward Euler method to the backward Euler method to the Crank-Nicholson method. So we'll start with forward Euler. So let's make a plot of space versus time. And so spatially, we can picture we have some array of values for, say, y. And so that would be like y, and then y prime would be like the next value of this array of values. And you know, there was like a lot of things in here, 100 things in here. And so the idea here is if we want to find, say, this new value of y, call that at element I, as opposed to I plus 1 and I minus 1, which are its neighbors. What we need to do ultimately there is look at 3 of the previous values. So we're looking at basically I left and right is the sort of names we've been giving these things. And so then we take those 3 values and we do a little bit of algebra, and then we calculate the next value. And the advantage of the forward Euler method is this is relatively easy to do. You're just looking up old values, doing some math, getting new values. But as we saw, that this can go wrong sometimes. That you can have a case where like the errors are basically building up every step, and then your solution explodes. So let's look now at backwards Euler. And backwards Euler has the advantage that it's not going to explode, but sometimes you get the opposite where your solution decays away to be 0. Sometimes that's okay, sometimes that's preferable, or maybe it happens at a different time scaling and you can get away with it. But what backwards Euler does is it doesn't give you just a single value, but instead you end up getting 3 values at the new time step using 1 value at the old time step. Basically, it's like, well, that's why it's called backwards. It's backwards. So from 1 value, from say old location I, you end up getting new location I plus 1, I, and I minus 1. And so what happens here is you are getting a set of equations, because now if we look at I plus 1, it depends on its neighbors and so on. So you have to solve simultaneous equations. It's basically at every time step you have 3 simultaneous equations. And now there's ways to solve simultaneous equations. Solve banded is a nice way to do that. Okay, but we still have an issue here where we tend to lose energy. So actually, let's go write down these problems. So forward can explode. It doesn't always explode, but it can explode, depending on what equation goes into it. Backwards Euler could decay away to nothing. And then we have Crank-Nicholson, which doesn't have either problem, right? And so it seems like, well, this is spectacular. Let's always use it. The only problem is it's really painful to set up. So we're going to see how to do it in cases where we have to do it. The idea with Crank-Nicholson here is we are going to average going forward and backwards, which is kind of like a midpoint rule if you think about it, going forwards and backwards. So what we sort of do is it's kind of like we calculate an intermediate point between time steps, and this helps our accuracy. So we take a total of 3 points from the old array to create 3 points in the new array, but we go through an intermediate time step. So we go sort of like a forward Euler to get to that intermediate step, and then we do a backwards Euler to get to our final result. And the end result of all of this is that helps your accuracy, and it gives you something that's stable. Okay, so now if we think here, let's do a different color, like in terms of the mathematics. So forward Euler is like saying that y prime, that is to say y new minus y old, divided by step size h is equal to some function on the right hand side, and we can rearrange that to solve for y. Backwards Euler, the difference between old and new, is equal to the new value of f prime, and that's a little bit painful because we kind of have to know like where do we end up. This manifests as having coupled equations. And then Crank-Nicholson looks like y prime minus y on h is equal to the average of f and f prime. And this gets rid of those terms that tend to misbehave. The term that explodes and the term that decays, in some sense, cancel each other out. And then just to be clear, notation-wise, when I say f, that's like the right-hand side of the differential equation, that would be a function of x and time. Whereas if I say f prime, I don't mean derivative here, but I mean taking a time step ahead. So I'm using primes here to represent future time step. So let's look at an example. Let's build on that wave equation. And so I'm going to work out the backwards Euler in detail because it's got all the same nastiness as Crank-Nicholson, but it's a little bit cleaner. And then I'll show you the result for Crank-Nicholson, having talked about how we do it. And then ultimately, we'll go back to our notebook and see if we can fix the wave equation. So the wave equation itself relates a second partial derivative with respect to time to a second partial derivative with respect to space. Okay, so regardless of what kind of method we use to do the time part. The space part is still going to be set up using a finite difference. So what we're going to end up with here are two equations, since we had a second order in time equation. dy dt will be equal to v, nothing fancy there. We don't have to do any finite difference in that case. And dv dt is equal to c squared on a squared. So a squared will be like our spatial grid spacing. And then what we'll do is we'll take like, this would be like y to the left, y to the right. Maybe it's right and left, doesn't really matter. Times the original. And then, just to be clear here, I'm being a little bit more compact with my notation because we already have a lot to write. Y sub I is y at location and time x and t. I plus 1 is kind of like on the screen I just erased. So that would be a step ahead, so x plus a and t. And I minus 1 would be at x minus a and t. Okay, so that's what I mean here with these subscripts. Think about these as like elements in an array. Okay, so now we want to do a backwards Euler. So what backwards Euler says is that yi prime, so prime means new, not derivative, but the new value of yi is equal to the old value of yi plus h vi prime. Okay, so like this is our first equation here, and the vi prime, meaning we kind of have to look ahead and sort of already know what vi's prime is going to be. How do we do that? Well, from the other side here, we're going to get vi prime is equal to vi, so at the previous step, we're going to have an hc squared on a squared, so that's just h times this coefficient here, and then we have the rest of the stuff in the future. So even though this version doesn't have primes in it, we're looking into the future. So this version does have primes on it. These are future steps. Now at first this seems like impossible. How do we know a solution if we have to already know the solution? But what we actually have here are, these are simultaneous equations. Like we can plug one of these equations into the other. Okay, so let's do that. Let's make the substitution. And what we basically just get is an equation that couples y and its neighbors. So plugging the second into the first is going to give us the equation yi prime is equal to yi plus h times this equation over here. So h times vi in the past plus, this is going to become now an h squared, c squared on a squared times yi plus 1 prime plus yi minus 1 prime minus 2 yi prime. Okay, and then we just want to rearrange it to make things a little bit cleaner. Since we have all these coefficients here, let's just squish them into a single variable that I'm going to call k. And if we rearrange to basically get all the y primes on the left-hand side of the equation, we end up with negative k times yi minus 1 prime plus 1 plus 2k yi prime minus k times yi plus 1 prime. Oh, don't really need parentheses. And then on the right hand side of the equation, we are going to be left with just this stuff here. So that's a yi plus h vi. Okay, so this is in the form that we could write as a matrix equation. And its matrix equation is two-dimensional because not only do we have these neighboring values of y in space, but we also have to do this for every time step. And we were trying to solve then this sort of like two-dimensional equation. So as a matrix equation, we have something like this. So we have some like coefficient a1, a2, and then it's all zeros. And then on the next line, it would be like a2, a1, a2. And then it'd be of the form a2, a1, a2, and then, so on. For as many time steps as we have. All that acting on the y prime is equal to b. And I know I just erased it, sorry. Bad spacing here, but what we had is like down the diagonals, that's going to be the term that looked like 1 plus 2k. And then off diagonal, we have terms that look like negative k. And then on the right-hand side, that's like the right-hand side of the, over here, the right-hand side of the equation we just wrote, that was equal to yi plus hvi. Okay, and so this is the kind of thing that we can solve using some kind of linear algebra, like solve banded, if we're doing this in Python. Okay, so we're going to solve this for y prime, and again, y prime is like an array. So it's got, you know, a bunch of, each column here would represent an element of that array. And then once you've done that, we still need to finish our set of equations, so we can come back and get vi into the future by using vi in the past plus k on h times y at I minus 1 plus y at I plus 1 minus 2 times yi, which was just one of our original equations. And you know, once y prime is known, then we can plug those in over here and get v. We don't have to do any matrix stuff. So that's what backwards Euler looks like. We have this sort of extra step with the linear algebra because we end up with each neighboring grid point being coupled. Crank-Nicholson is pretty similar. And so what we're going to get here, just going to give you some important like signposts along the way of doing the same derivation for the wave equation. The equations we write for vi prime and yi prime. So we're going to have, if we're here for y, we're going to have yi in the past plus h on 2 times vi plus vi prime. So with the forward Euler, we would have h times vi. With backwards Euler, we had h times vi prime. With Crank-Nicholson, we average them. Same kind of thing will happen over here for the v equation. We're going to have an hc squared. There's going to be a 2 because of our averaging on a squared. And then over here, it gets messy because there are 3 terms times 2. So there's going to be a total of 6 terms over here to the right. So we're going to have yi plus 1 plus yi minus 1 minus 2yi. And then we do the same thing with the primes. yi plus 1 prime plus yi minus 1 prime minus 2yi prime. Okay, and then you rearrange all that, and you'd end up here with the set of equations. Looks kind of similar, just with extra terms. So we're going to have some constant k, which just holds all our coefficients, times y at I minus 1 prime, and then we're going to have 1 plus 2k yi prime, and we'll have minus k times yi plus 1 prime. On the right-hand side, we're going to have k times yi minus 1 plus 1 minus 2k yi plus k times yi plus 1, and then finally plus hvi. Okay, so you can see we kind of like, we have more terms on the right-hand side. And then over here for vi prime, we're going to have, I mean, it's actually just exactly this line again. So we're going to have vi plus, this would end up being a 2k on h, yi plus 1 plus yi minus 1 minus 2yi plus yi plus 1 prime plus yi minus 1 prime minus 2yi prime. So just like we had before, where we, in this case, end up defining this constant as h squared times c squared on 4a squared. Of course, the constant k here is not an important part of the method. It just makes this look a little bit cleaner. It's already pretty awful looking. And of course, like with the FTCS method or even the relaxation method, if we change our partial differential equation, we get to do all of this all over again and get a new set of these coupled equations. Once you have them, however, it's solve banded, and here's your coefficients. And well, let's just try that out in the notebook and see how we can solve our wave equation and get something that stays stable for a long time. So here we are back in the notebook, and I've already typed up the result we just found, which is this sort of set of coupled equations for y and v. And I'm going to use k here as a simplifying factor. Keep things looking nice. I've also copied our code from up here when we had the exploding wave. And just to show you where we would make changes. Okay, so the constant C is the same. Our spatial grid is the same. I'm going to make some changes to time because since we're making something stable, I want to make sure it stays stable. So I'm not going to animate anymore, but what I'm going to ultimately do instead is I want to plot the midpoint of the wave, which should look like a sine function as the midpoint goes up and down for a very long time. So let's go for 100 times more time. Now that means that if I'm going to keep the same spacing here, like if I multiply the numerator by 100, I also have to multiply the denominator by 100. So I'm not making my spacing different. It's the very same spacing, I'm just doing a lot more points. Likewise up here, this would become 10 to the 5 plus 1. So it's just 100 times more time. Same h. Okay, so this is just really to check stability. Same initial conditions. We want to make sure we reset them, of course. And then in here, we're going to have to make some change. So appending y.copy is fine, but everything after that is really not useful anymore because that was the forward Euler method. Okay, so now the new changes we're going to have is we are solving a matrix equation. In effect, if we look here to find new values of y at I minus 1, I, and I plus 1, I have to use old values of y at I minus 1, I, and I plus 1. Okay, so in other words, I have to find all three of these. I find three y's at the same time. And so this is a matrix equation of the form matrix A on the left equals vector B on the right. And then once we have that, we can just plug our values in to find the new value of V. So the matrix A here depends on these coefficients. It's got a coefficient negative k along the off diagonals. And at the diagonal, it's got a coefficient 1 plus 2k. So this never actually changes. K is fixed. It doesn't depend on what time step we're on. So we can set that up ahead of time. Okay, so let's define what k is, our little helper bit here of math. So that's a quarter times h squared times c squared divided by a squared. Okay, and then we're going to make our banded matrix. So that would, let's call that matrix A, and we'll make A1 be the diagonal. So that was equal to 1 plus 2 times k. That's this coefficient right here. And then A2 are the lines above and below the diagonal. So their coefficient there is a negative k. And then we're going to create A itself. I will start with what's mostly zeros. So we'll set it mostly to zeros, and then it'll be a 3 by 99. Okay, why 99? That has to do with the fact that we have 101 points and we are leaving the boundary conditions alone. So 99 is equal to 101 minus 2. And then 3, because we're going to use solve banded, so it kind of wants us to pack just the diagonals into an array. Saves us a lot of memory in our computer. We could probably get away with just building a big 100 by 101 by 101 matrix or 99 by 99 matrix. That would fit in our computer's memory, but it's not really. Just because you can do something inefficient doesn't mean you should if you have a better way. Okay, so the first row would be A2. The next row is the diagonal. The caps lock there. That is the diagonal, so that's A1, and then A2 again. Okay, and so that's going to be what goes into solve banded. So this will be that diagonal array in solve banded, and then we need to have another side to our equation, which will be this right-hand side here, but we have to do that down in the for loop because it keeps changing as y changes. So that happens down in here. So we're going to do b here is equal to, can't quite fit it all on screen. I want b here to be this right hand side. So b is going to be k times y, and this is the like a sliced y. So that would be like, I'm not sure if it's the 2 to the end or the end to the -2. It doesn't really matter because it's symmetric. Anyway, so then we will add on a 1 minus 2k for the next term. And that's going to be y just without its boundaries. And then we have here k times y 2 to the end, and then plus h times our v. Of course, we want to make sure we are not including the boundary conditions there either. Okay, so now with that, we can do our linear algebra. So we're going to get a new value for y using SciPy as linear algebra, which actually I don't think I have imported that one. So let's make sure that's in there. Whoop. Okay. Okay, we're going to use solve banded here. Remember the way solve banded works. It wants to know how many lines are above and below the diagonal. It wants this diagonal array that I'm calling capital A, and then it wants an array B. So there was one line above and one line below the diagonal. I've already built array A, and it never changes. And then I need to use B, but B is going to change step by step. Why it's in the for loop. Okay, and then we can set what V is going to be equal to. That would be this last line here. We don't have to do any fancy matrix stuff for it because we've already calculated values. Now do watch out. It uses new values of y and old values of y. New values of y are currently stored in a variable named y. I haven't stored any old values of y, so we should do that. We'll call it y old, and that's equal to a copy of y. And be careful that you copy it. If you just set it equal to y, that makes y and y old always identical. And as y changes, y old changes, and that leads to broken stuff. Okay, so again, I have the issue where I can't quite get everything to fit onto the screen at the same time. Let's just make a copy of that cell. Oh, it doesn't want to copy. C for copy, V for paste, right? There it is. So it's underneath and I can still see it. Okay, so then we could do this one as a plus equals because V new has a V old right on the right hand side. Then we're going to have a 2 times K divided by H and then multiply by Y old. Go up to -2 there, plus Y old around the middle. Oh, no. Skip the term. We have a -2y in the middle, or y old in the middle. And then we have the same kind of things, but they're y's instead of y olds. Actually, I guess I wrote them in the wrong order. No, I mean, this doesn't matter, it's addition. But if I want it to look just like the way the math is, these first ones are the y's and the second one the olds. Okay, and of course, by far the hardest thing is like not making a typo when you type all this stuff in. But it'll be easy enough to tell because our solution will be nonsense if I type the wrong stuff in. So once all this is calculated, I want to check if we are stable. So the way I'm going to do that is I'm going to first of all take shape, which is a list, and I'm going to turn it into a 2-dimensional array just because that makes it easier to work with. And then I'm going to plot the middle of it for every value of time. So now that it's a 2-dimensional array, I can slice it like an array and always grab, this will be the middle element of the array, the middle spatial element at every time. Okay, so let's see. Does this run? It's going to take a little while, and if it does run, does it make a graph that is stable? It ran, And it made a graph that was stable. So somehow a miracle has happened and I didn't make a typo here. Well, I guess not, because it looks like it's oscillating, and it even after oscillating a lot of times, you can see there's like no change in amplitude, no sign of any instability. So this is why the Crank-Nicholson method is worth it, is it gives you stability in problems that would become unstable. You just use the straight FTCS method. This is never your number one first attempt. You would always try it with FTCS because it's a lot easier to write the code. Runs faster too. But if that doesn't work and it does something insane like explode, like our spring example did, that's the sign of instability. And in that case, then you go to something here like Crank-Nicholson.